Okay, hi everybody. My name is Mathilde. I'm so excited to be here. Is there interference? You guys have to tell me. A little bit? That's good. Okay, so I was asked to come here today by the wonderful organizers, which I'm so thankful for. Thank you for having me, to give you kind of a broad introduction to graph neural networks. You might notice that the title of my slide refers to topological deep learning. That's sort of my area of expertise. But what I want to do today is kind of a mashup of both, where we'll go over the basics of GNNs. If you're not familiar, this is just going to be like the building blocks of how we process machine learning on graphs. And then once we've got that in the books, I'll move on with my area of expertise, which is TDL, which I hope you'll find just as interesting. So, cool. These are some of my collaborators whose work I'll be featuring today. As you know, no research is done alone, so I will be thanking them for all of their contributions. This is kind of my outline for today. We'll do GNNs first and then TDL. Just show of hands, because we've been learning a lot about LLMs and RL and diffusion so far, and maybe not so much this kind of stuff. Who here has worked with a GNN before or read about them, is familiar with them? Great, okay, good show of hands. So hopefully this will be useful to you just as like a reminder of what the building blocks are. I know I learn when I go back to the basics like this, and hopefully you'll find some intuition there. And if it's your first time dealing with GNNs, well, I hope that you walk away feeling like you learned something. So let's start with part one. I will preface this by saying that I'm not going to go super in-depth with the math. We'll just go over the necessary building blocks. If you want to learn more, these are all really great resources. A lot of them have come out of Google, actually, that I highly recommend. Okay, so graphs are all around us. We exist in social networks that have relationships between people. We could draw a graph of everybody here today and how we're related to each other. You can think of the molecules that make up the world. Inherently, the bonds between the atoms are really important characteristics of this data. That might seem kind of obvious, but when it comes to doing machine learning, it's important to remember what the fundamental characteristics of our data sets are. And social networks and molecules are really good examples of data sets whose connectivity is really important. So maybe you've heard these examples before, and in honor of Google sponsoring this, DeepMind, I wanted to throw up a couple of examples of work that they've done with graphs. Maybe you saw this paper that came out last year in Nature Communications on football or soccer strategy using GNN. So they were drawing graphs between the players on the field and trying to optimize strategy for like the best possible corner kick outcome. So that's a kind of a cool graph example, as well as traffic. So Google implemented GNNs in Google Maps, and it led to increases in accuracy of ETA prediction. So if ever you're using Google Maps and you're like, how does it know the exact time that I got here? Like, it's so accurate. Well, GNNs have a role to play in that. So maybe that gives you an idea of why this stuff is really exciting. Let's dive into what GNNs are, what we do. So the most important ingredient in graph learning is considering the graph connectivity. So instead of just sending in our node features, we also have to consider the edges between those nodes and respecting the permutation invariance or equivariance of the graph. Who knows what permutation invariance or equivariance means? Okay, a few hands. So this means that when I send in my node features, I'm sending them in an order, right? There's one node feature that comes first, second, third. It's really important that my neural network, whatever it is not fundamentally affected by the order in which I send in my nodes. So whether I order my nodes like this or like this, my output shouldn't fundamentally be different. We say that a model is permutationally invariant when the output doesn't change at all after permutation. And we say that it's equivariant when the output is equally permuted. So that's actually a really important property of graph neural networks. It's why we say that they respect the symmetry of the graph. Okay, so now that we have our two ingredients, let's figure out how to build a GNN. Let's take a step back and go to a model that we might be more familiar with, convolution. So in convolution, we have a kernel, right, that slides over our, in this case, 2D image and takes the dot product, and that is our ultimate representation of the data. So our kernel is what we call translation equivariant, which means that regardless of where the feature is in the image, it will be processed as equally important, right? It's object, like the placement of the object in the image, whether the cat is top right or bottom left, doesn't change the fact that it's a cat. And the other important property of convolution neural networks is that they consider the locality or connectivity of the pixel. So in this case, every single pixel, right, is being summed to ultimately its 8 surrounding neighbors. So in a weird way, it's almost as if we had a graph with every single pixel connected to every other pixel in its immediate surroundings. So maybe you can see where I'm going with this, but once we have these two ingredients, we can ask, okay, well, how do we extend this to graphs? If instead of an 2D image, I have a graph, what does convolution look like? Now, remember, we want it to be permutation equivariant or invariant, and we want to consider the connectivity of each node. So what can this operator look like? We need a really important tool to define this operator called the adjacency matrix. Who here has heard of an adjacency matrix before? Okay, great. So the adjacency is simply recording which nodes are connected to which nodes. There's a 1 if the nodes are connected in the graph. There's a 0 if they're not. Caveat here that this is what we call an unweighted and undirected adjacency matrix, meaning that all of our edges are equally weighted. One is not more important or has a different feature than the other. And the graph has no directionality to the edges. So, for example, our red node isn't exclusively sending information to our orange node like you might have in a traffic network, for instance. Okay, so now that we have this important tool defined, let's go back to figuring out what our operator is in our convolution on graphs. Now let's sort of visualize what we're sending in here. We're sending in our node features, which is just like a stacked feature matrix, and our adjacency. I propose that we do something like this, where we're going to multiply on each side of our feature the adjacency matrix and a matrix of learnable parameters, W. Effectively, what the adjacency matrix is doing for us is it's kind of selecting which nodes get to talk to which nodes, which effectively recreates the connectivity of the graph. So what output does this give us? What it's doing is taking each neighbor of each node and summing it. So this red node becomes the sum of the yellow and blue features, and the process repeats across the graph. That's it. That's all that's happening. We are now aggregating information across local neighborhoods of each node. Great. Are we done? No. This is the basic operator, but there's a couple issues with this. First of all, you see a learnable matrix. We probably need some nonlinearity somewhere in this layer. That's correct. So we will add a nonlinearity. Another issue that's kind of weird here is that our node features that we have in our output don't actually depend at all on the original feature at that node. That doesn't make a whole lot of sense. So we are going to modify our adjacency matrix a little bit with the identity just to keep that original node feature in the loop. And lastly, you might be looking at all these sums, and you might think, these node features are going to be way bigger, right, than my original representation. So we need to scale. And to scale, I'm going to use more regular mathematical notation, and we're going to call the features of the graph H, and the updated features H prime. And this is what we currently have. Now, instead of just using the adjacency matrix and the weight matrix, I'm going to scale by what we call the degree matrix, which counts the amount of nodes that each node is connected to. And with that, we have our first graph convolutional layer. We call this the mean pooling layer. It's really strong for inductive biases. This is how you write it at the node level. So if you were to consider only one node, like the red node, that is the updated feature after one layer. There you have it. That's your first graph convolution. You might look at this and think, okay, great. Can we make this better? Yes, absolutely. So the first thing that you can consider is the scaling. So let's say we pick the red node. Right now, we're only considering the size of the neighborhood of the red node in our mean pooling layer. What if instead we consider the size of all the neighbors to all the neighborhoods of the neighbors to the red node? So for example, not just the size of the red node, but the size of the blue node and the orange node. And that leads to this, which is, ta-da, the graph convolutional layer from Kip and Welling. This is like the most famous graph neural network. It sort of kickstarted everything and is what we typically use as like the MLP of the graph world. So hopefully this kind of like walked you through how we get to this kind of GNN, and you have like a little bit better intuition for what's going on. Great. We're not done though. If you look at this, you might think, wow, this is really restrictive. I'm exclusively doing sums and means, and there's nothing very expressive about this. And you would be totally correct, which is where message passing neural networks come in. So these came out in 2017 and also rocked the graph world. And I know this sounds like forever ago, but it's still super foundational to what we do. And I will go over it really quick, and hopefully it will set the stage for the rest of my talk. So this is our GCN message passing equation. We want to make it more expressive. We want to make it more flexible. So instead of this like very rigid weight times feature normalized message, we are going to define any possible message between two nodes as given by this function m. Function m can depend on both features of the nodes. It can depend on a feature on the edge. It can depend on a learnable weight. It can be anything, right? This is what we're going to use. And then we're also going to define a general aggregation, not just a sum. So that's what that looks like. Finally, we're going to make this a more general readout and define some broad update function. And there you have it. That is a message passing neural network. It is very expressive and has been really powerful for data sets that have graphs that can be hard to distinguish. If you have, for example, a bunch of molecules that look almost the same, but they're not quite the same, we call them isomorphic. These neural networks are really powerful in distinguishing them. So that is sort of my introduction to GNNs. Hopefully you got something out of that. Just to recap, this is what a graph neural network looks like. At each layer, we perform one iteration of message passing, and we're basically kind of circulating the features around the connectivity of the graph, updating those features, and repeating this process until we achieve some representation that we can extract a prediction from. What kind of prediction? Great question. We can do a node-level prediction, an edge-level prediction, or a graph-level prediction. These are all kind of different tasks, and we can consider some examples of each. So coming back to my original examples of like the social network, you could ask something about the person specifically, a relationship between two people, or something about the group at large, and similarly for the molecule. Okay, There's an issue here, though. Are we 100% sure that the connectivity of our data is fully encapsulated by pairwise relationships? What if higher order relationships, such as rings, like carbon rings in the molecule, or groups, like all the folks from Mila that are here, matter in the data set, right? What if these are inherent properties of our data, fundamental to the structure of our data, that we are currently throwing out the window by exclusively relying on pairwise connections to circulate information in the graph? Just to recap, this is what's happening in one layer of a traditional graph neural network, and each of these updated node representations is exclusively informed by the pairwise neighbors of these nodes. Now, you might say, what if I have multiple layers of my graph neural network, and by doing multiple hops, right, k hops, I am effectively aggregating information over multiple neighbors? I would say that's true. However, you are relying inherently on pairwise connections of your graph to get you there, right? If you have a ring of 4 atoms, you need at least 4 hops for your network to see this ring. And also, 4 layers deep, who knows how much information of the first node you'll have actually kept, right, by the time you get to the end of your ring. So we are losing a ton of really important information with GNNs, and this is sort of an important realization that the field had 3 or 4 years ago, and topologists said, we might have an answer. And that brings me to part 2, which is topological deep learning, which has been shown to be really important in many, many applications, ranging from how we move, how our brains work, how space works, and how the internet works. Before I move on to TDL, does anybody have questions about GNNs or the broad intro so far? Yes.
Nice introduction so far, because I know nothing about GNNs.
Oh, great.
But I was wondering, what if there are hidden connections that we already assumed that maybe doesn't exist, and then we go on with our network and we still haven't captured these hidden connections between the nodes? How can we take that into account?
That's a great question. When we talk about building these connections in the first place, a lot of that is data pre-processing and just comes with the data set that you were given. It's really important to have flexible and expressive networks for that exact reason, to allow your network to learn hidden information. However, like I was saying before with the GNNs, when you're only using pairwise connections and you maybe say you have a hidden connection that's really important, you really are crossing your fingers that you're going to retain enough information, enough expressivity to capture that. So I think TDL is actually a great alternative because hopefully you'll see we can access more information with less features. Okay. Okay.
I was wondering about the higher order solutions to the higher order problem. I mean, is it just maybe a problem of representation because the graph is inherently representing one hop? So if you wanted to represent data that should also
Yes.
model like higher order connections, why don't you, for instance, add an edge also between not only the neighbors but also between the 2 of neighbors, and then weigh the edges differently. So like weight 1 would mean it's immediate data neighbor.
Yeah. 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 So you're describing one of the domains of topological deep learning, which are called hypergraphs. Yeah. It's both. It's both. So you need to represent your data well, and that's kind of a little bit of just an empirical choice that you make. But then you also have to have a neural network that can process information on that domain. If you send something higher order into a GNN like the one that I described, it will not be capturing the adjacency, the connectivity beyond the edge-wise hops. Hopefully that'll make more sense when I actually get into TDL. So I'll move on.
Oh, sorry, I have another question. So basically, I'm here.
Yeah. Oh, hi.
So your graphs are like all the nodes are fully connected. For example, there are some graphs like I have a big graph, and there are some islands, small subgraphs, or even orphans. How to deal with those graphs?
Sorry, what do you mean by like add-ins?
It's like I have a big graph and some small graphs, but they don't have edges between each other.
Oh, that doesn't matter. Your adjacency matrix will just have zeros between the nodes making up those graphs. I could pass a graph to my neural network that is in fact a million small graphs and it wouldn't know any better.
Okay.
Okay, one last question and then I really do have to move on to TDL.
I'm also like a quite beginner to the graph neural network, so that's why I wanted to ask, when you train them, how do you know when to stop? Is there like some notion of entropy that you follow? And I can also imagine that some of the, if the graph neural network is a simulation of, I don't know, traffic or something like that, then that can be like circular, as in like you may reach the point when it just repeats itself, and how do you capture that?
Yeah, so that's a really important problem actually in the field called over-smoothing or over-squashing. And it's when you have too many layers of your graph neural network and all the information is circulating, and eventually everybody kind of has the same information, right? And you've sort of collapsed everything into a mean. And for that reason, graph neural networks really can't go deep because you lose a lot of information. So, I mean, often this is empirical, but people will keep very few layers of their GNN and then check to see that information is preserved through the distribution of information on the nodes. So yeah, exactly like a measure of entropy. There's been a lot of research in GNNs since these like means and sums. But TDL is a great alternative because you're no longer relying on these pairwise hops to get from one place to another and sort of squashing information as you go. Through higher order relations, you can send information from one end of your graph to the other and maintain expressivity. So that's actually like a really active problem that people have been trying to solve.
Cheers.
Cool. Okay, so I will move on. If you have any other questions, either come find me or we'll go after I do TDL. So topological neural networks, maybe you've gotten this by now, generalized graph neural networks by representing and leveraging higher order relations. What do I mean by higher order relations? Well, it's exactly the same as a GNN, except now instead of only having pairwise connection between our nodes, they can be n-wise connected, whatever that means, and we can also define hierarchy between our nodes. I can say, this is an edge, this is a face, this is a volume. This concept of rank, or like dimensionality, is introduced into what was before a very flat graph. So that's what a TNN looks like. It's really not that different from a GNN, but we have to be careful about how we represent this data and how the message passing operates on this domain. Okay, here are the domains. So I mentioned them earlier, but in TDL, there's a bunch of different ways that you can lift your data from a traditional domain like a set or a graph to a higher order domain. First of all, there's the geometric domains, the part-whole domains, which are adding faces and volumes in like a constrained geometric way on top of your graph. So you can imagine filling in faces, filling in volumes, all nicely bounded by edges. Does that make sense? Okay, that's category one. Category two is set type relations, which are much more flexible. In this case, you don't need to have really rigid edges that are bounding every single higher order relationship. In this case, any node can be connected to any node which kind of reminds us of the K-hop neural networks, which you can re-express this as. However, we have no concept of hierarchy here. Even though our edges are really flexible, they're still all edges. We don't have faces or volumes, and so on. Which is where the belle of the ball, the combinatorial complex, comes in. This is algebraic topologists' bread and butter. It is the most flexible domain that incorporates both set-type relationships and part-whole relationships. You can truly go crazy in this domain. You can call anything a face. You can call anything a hyperedge. There's no limits, and people get really creative adapting this domain to their application-specific needs, whether that's, cosmology or the internet or whatever. So this gives you an idea of the domains that we're going to be operating on. I'm not going to specifically go through each domain, but keep that in mind when we do examples, that it could work on any of these. But to keep things simple, let's just look at real-world applications of what they look like. In the part-whole case, we're really talking about geometric relationships. So in a molecule, you would have the faces of the molecule colored in as features of the molecule. So you no longer only have nodes and edges, you also have rings, such as cyclopropane, which is an inherently important feature of your data. The cellular complex is a little bit more general because it can accommodate more than just triangles. That's the big difference. And then in the hypergraph case, this is useful for interaction type data sets where any protein could be meaningfully interacting with any protein in your body, and you might want to be able to represent that. And then the combinatorial complex, you can do both, right? You can have these conceptual high-level interactions as set type and the rigid geometric ones as part whole. Okay. What do these higher order relationships look like in practice? So the first step is lifting our data. This is a really important pre-processing step. It's a whole field of how do you lift in the best way possible, given your data set, given your downstream task. In this case, we're just going to imagine that we have a graph and we have an algorithm that fills in the rings of the graph, and that gives us our higher order domain. Just quick terminology. The higher order domain is made up of cells. A cell of rank 0 is a node, rank 1 is an edge, rank 2 is a face. I'm just going to be using the word rank, so that is what that means. Next, we're going to determine the connectivity or the neighborhoods that exist on this domain. We did that earlier in the graph case with the adjacency of the nodes, right? We determined how we consider our graph to be connected. We have to do it again here, but now we have way more going on, right? We also have edges that are connected through faces, and faces potentially connected through volumes, and so on and so forth. So we need to be a little bit more careful as to how we define the connectivity or the topology of our domain. So what does that look like? Well, there's 4 possible neighborhoods that people use, and I'm going to go over them a little bit quickly. Hopefully, it will be somewhat intuitive. The first, most important neighborhood is the boundary. This is the building block. It's the Lego block of all neighborhoods. The boundary of a cell Y is all the cells X of lower rank that we determine to be bounding that cell Y. So for example, the boundary of this edge Y are the 2 nodes, oh, you can't really see, whatever, the 2 nodes X that are not really showing up very well on the slide. The boundary of that face Y are all those edges X. Okay, that's the boundary. The co-boundary is the same, except instead of going down a rank, we're going to go up a rank. So the co-boundary of this node Y in the top left corner is all the edges X that are touching that node Y. And similarly, the co-boundary of this edge Y is this face X. Now we're going to use our Lego block, the boundary, to define our adjacency. The first one, which is what we did earlier on the graph, is what we call the upper adjacency. It is connecting edges through, or connecting cells through upper ranks. So it is connecting nodes through the edges between them. Okay, sorry, my colors aren't really showing very well. Let's look at this example. So this edge y, we say is upper adjacent to those edges x because they all share a face, right? It's like what we did on the graph. We took nodes, we went up a rank through the edges, back down to nodes. We're doing the same thing here, except on arbitrary rank r. And you can imagine doing the same thing with lower adjacency, where we are not going to go down a rank. So our edges are going to be lower adjacent to all the edges that they share nodes with, and our faces are going to be lower adjacent to all the faces they share edges with. Did everybody follow that? It's a little bit dense. Show of hands, please. Awesome. Okay, sort of. So we have 4 neighborhoods. Some of them are going up ranks, some of them are going down ranks, and some of them are going to the same rank, but either up or down. Just to connect this back to what we saw earlier, the graph has one neighborhood. Well, it has one adjacency, and it's the adjacency of the nodes. It is the upper adjacency of the nodes. That is kind of all we have access to in the graph. With TDL, we have access to all this new kind of rich connectivity across arbitrary rank. So hopefully that gives you a hint as to why these models are much more expressive. Okay, now let's talk about message passing. Exactly like in the graph neural network, we can define an arbitrary message between cells, except now, instead of the cells all being nodes, the cells can be nodes, they can also be edges, they can also be faces, and how they pass information to each other can either be convolutional, attentional, or general, exactly like you would expect in any other neural network. I won't go into that too much, but just know that there's like these options of message passing. Putting all of this together, let's imagine one layer of a topological neural network. You start with a node H, right? We want to know how to update the feature on that node H. The first thing you have to do is pick your neighborhoods. Your neighborhoods are the cells that you consider to be connected to this node. It is arbitrary. It can be anything you want. It is typically built from the boundary. So these are 3 examples of neighborhoods to that node. Once we have our neighborhoods, we're going to look at the cells inside each neighborhood, and we're going to pass a message, right? Every single node in neighborhood 1 is going to pass a message. That message can be attentional, can be convolutional, whatever. Every single face in neighborhood 2 is going to pass a message, and so on and so forth. Once we have all of these messages from all of these neighbors, we must aggregate them. So for each neighborhood, we are going to combine these messages. That can be a sum, it can be a mean, it can be a max, doesn't matter. This is exactly like what we had in GNN. However, unlike in the GNN, we have multiple neighborhoods. So I also need to add an aggregation step to combine these neighborhoods together into one message. So that is a second aggregation step that we did not have before. And finally, we have an update, which might depend on the original feature on the node. So that is one layer of message passing in a topological neural network. Hopefully, it kind of makes sense as a general extension to what we saw before with GNNs, except with more neighborhoods, basically, and more ranks. Okay, so just to recap, this is what we had before, the graph message passing neural network. This is the equation we came up with that's oh so general in the graph world. Now, what does this look like in TDL? Well, we've added an aggregation step because now we have multiple neighborhoods, right? And also, our message ij is not only between nodes I and nodes j, it's between any cells I and j. And that's it. That is our official equation for what happens in a layer of a message passing topological neural network. Okay. So, yeah, I guess I should have done this earlier. You can see here how the equation breaks down into this figure step by step. what does this all look like in the literature? This is kind of dense and abstract, and I want to show you that there's so many different implementations of this and so many different uses to this. So we are going to compare models by what happens in one layer of message passing. And at the start of my PhD, I spent many months of my life rewriting the message passing equations of all the models that existed at the time in one shared notation, because all the papers in TDL tend to use different notations sometimes, which is incredibly annoying. So if we wanted, we could go over all of these equations and all of these domains and really nitpick what's different. However, that would take forever. So instead of doing that, we are going to visually represent what happens in one message passing layer. I'm not sure what's happening with the mic, but let me know if it bothers you. So here we've got one layer that we're going to represent as our input features and our output features. So we're going to say all the nodes are represented by those like yellow circles, and all the edges are represented by those pink circles. And we are going to fully represent a message passing layer as the arrows between those features. More specifically, we're going to say that the color and boldness of that arrow represents the type of message passing going on. And we are going to write down the matrix notation representing the neighborhood that those cells are passing information to each other from. So like the adjacency, the boundary, and so on. And finally, we are going to represent our aggregations as either a simple arrow, which means a sum, or a little banana, which represents. Okay. So, now that we one model with one tensor diagram. Oh. Up now. Okay, thank you for letting me know. Okay, so in the hypergraph world, people like to do a whole lot of nodes to hyperedges back to nodes, which comes back a little bit to what you were saying earlier, I think, when you're asking about K-hops and GNNs. And you can do this in many different ways with many different kinds of neighborhoods and aggregations and message passing styles. So this is like the closest to what a GNN would be, except now instead of just having edges, we have hyperedges that are aggregating information across multiple nodes each. And then you've got simplicial neural networks, which now we're working with faces. So the first simplicial neural network came out in 2020 and sent information from nodes to nodes, edges to edges, faces to faces. And then people started coming up with crazier architectures that do all kinds of funky stuff in one layer. And attention in simplicial neural networks started around 2022. Cellular neural networks are less popular. They're generally just extensions of simplicial neural networks. And finally, the combinatorial complex, which is the least explored domain, but the most general of them all. This figure is a little bit outdated. In the last year, there's been quite a bit of new development using combinatorial complexes. So that gives you an idea of what exists out there and how much exists out there in TDL. I want to spend a little bit of time, as I am nearing the end here, my last little section on graph-based TDL. And you might be thinking, why would we do that when I just spent so much time explaining to you why topological neural networks are more powerful than graph neural networks? Well, it turns out that in practice, TDL software is really hard to work with. It is a field that came a lot from math and signal processing, and not so much computer science. So the open source packages that exist out there for TDL are often pretty hard to work with, and has made it really difficult for the graph community and the ML community at large to interact with. So I have spent a lot of time thinking about how we can connect our field back to these packages that people are more familiar with. How about now? Okay, we're good. So if this wasn't the case and we had access to all these awesome packages, you can think of importing all the advances in the GNN world to TDL on these like higher order domains. So people have been thinking about how to do TDL using graphs. And previously what people did was use augmented Hasse graphs, which basically build graphs like this one by representing every single higher order feature, like these blue faces, as nodes. And then just like connecting everything using the adjacency matrix that would apply here. However, as you can imagine, this collapses a ton of information, right? We are collapsing everything into one big adjacency matrix, and we are losing the distinguishability between the neighborhoods. And that might not sound like a big deal, but if you work through like the expressivity proofs, it absolutely is a big deal. So this had some excitement, but still some challenges in actually doing real TDL on graphs, which motivates my most recent work from ICML called Topotune, which defines and implements graph-based TDL. So TDL that is fully like what I just showed you, the exact same equations and expressivity, except implemented with GNNs. So this allows us to use GNN software to do TDL. What's also exciting is that this is a super general model that subsumes the model landscape I just showed you. Basically, you can re-implement every single existing topological neural network as a GNN, is what that means. And you can work across topological domains. So in the past, you had to very early on decide that you wanted to work with hypergraphs or decide that you wanted to work with simplicial complexes. And there was no room for that to be a hyperparameter, if that makes sense. All of the code was built in a way that was deeply connected to your choice of domain, and that made it really hard to consider domain as a hyperparameter. So this is what Topotune looks like. It's a little bit crazy, but everything that's going on is that we are collapsing, or we're representing our higher order complex as a series of graphs, where each graph represents one neighborhood. It's as simple as that. So just like before, we are representing every cell in our higher order domain as a node, and then depending on whatever our neighborhood is, the adjacency between the cells, the adjacency between the edges, the boundary between the faces and the edges, whatever, you draw one graph for each of these neighborhoods. Once you have your graphs, you send them through a series of synchronized GNNs, which then output new representations on your nodes, on your edges, on your faces, which you then aggregate back into a single representation. So in this case, by representing my higher order domain into two graphs, I have now two representations per edge. That's not tenable. I need one representation per edge. So just like I would in a regular topological neural network, I'm aggregating across neighborhoods at the output of each GNN. So I have two edge representations that then become one. And that is it. That is a layer of message passing in a topological neural network, and we repeat that process for however many layers we want. And I just want to point out that this is an exact replication of what a topological neural network does. So steps A, B, C, B, C are fully equivalent mathematically to these steps portrayed in a like traditional topological neural network, which is really exciting because it means that we get to keep all the very fun theoretical benefits of TDL. We are not sacrificing anything by using GNNs. So that's really exciting. Everything is hosted inside TopoBench, which is the premier platform for benchmarking, developing in TDL right now. We've put a lot of work into this suite to make it as easy and as one-stop shop as possible. So we've got a bunch of data sets in there, a bunch of lifting algorithms. You basically pick your data set, pick your domain, pick your model, and you're done. So what this in practice looks like for TopoTune, this is what TopoBench looks like, is when you are picking all of these things about your model and your training scheme, you are going to pick your model to be a GCCN, which is what the model is in TopoTune, doesn't matter. And in your GCCN, you pick the parameters that you want. So for example, what GNN do you want to use? GAT, for instance. What neighborhoods do you want to use? And what domain do you want to use? And it is that simple. So compared to before with all the models that I was showing you where you kind of had to start from scratch and build these models from the ground up in a way that is like deeply tied to your choice of domain or deeply tied to your choice of neighborhood, these things now just become hyperparameters, which is like pretty game-changing and works really well. So we tried a like grid sweep of a bunch of different possible architectures using a bunch of different possible neighborhoods and domains and GNNs on many, many data sets. And it turns out that on the left-hand column here, I'm listing all of the models that we tried. So for example, a TNN using GAT, a TNN using GCN, a TNN using GraphSage, whatever. And we're comparing it to the best performing model in TopoBench at the time of testing on these data sets. And it turns out that in 11 out of 16 data domain combos, one of the GNNs outperforms the best performing TNN. So that's really cool. And what's also really cool is that it often uses way less parameters. One of the biggest issues with TDL is its complexity, its cost, because by introducing higher order relationships, you're naturally introducing cost. But by bringing things back to GNNs and leveraging all the advances that have happened in the GNN world, which is a much larger community, we can help reduce cost in TDL as well. So I always like to show you some examples of like what this can look like in terms of using it for any relational data that you might be interested in. If you've been working on a proteomics data set or you've been working on a social network data set and you already have a GNN that you really like, it's as simple as throwing it into TopoBench and boom, you've got a topological neural network. Similarly, if there's a data set that you have in mind, it's super possible to introduce a new data set and take advantage of all the lifting algorithms and the models that have already been implemented. So this can look like, trying different domains, trying different neighborhoods, maybe trying less neighborhoods, seeing if you can get away with less computational cost. Endless possibilities. And with that, if you're interested in doing some TDL, getting your hands dirty, getting open source experience, publications, we are about to announce the 3rd edition of the Topological Deep Learning Challenge. This is the 3rd year we're doing it. Every year it's a huge success, where we basically have this like 2-month hackathon for people to contribute to TopoBench in a kind of specific way. I think this year we're going to do data sets and lifting algorithms. This year, my advisor is offering an internship to the grand winner. So if you're a master's student in Europe and it's cold here sometimes and you want to come spend a few months in Santa Barbara with me, with the lab, participate in the challenge. And you never know, it's a paid internship. I think this is a really, really cool prize. And we're really excited to see what people can contribute. So this will be announced by Topology and Geometry in Data Science. This is their Twitter really soon. This is a conference that's going to happen right before NeurIPS in San Diego. You don't have to come to NeurIPS to participate, but you will get the recognition and you will get authorship on a paper if you just so much as submit. So that's kind of a really cool reward, especially for earlier researchers. So that concludes my talk. We went over GNNs, how they work, the sort of basic, most popular GNNs, and we built off of that to talk about TDL concepts, TDL literature, and some of the latest research in TDL that uses GNNs, kind of full circle. So that concludes my presentation. Thank you.